cross displacement, or FD sine theta. And here the important thing is that if an element is parallel or anti-parallel, then the angle is either 0 or 180 degrees, and the sign of those angles are 0. And here what do we see? The position vector r and the force are in the same direction. So the angle is 0, which means that no torque can be produced on this mu. If no torque can be produced in this mu, then we look to the second definition of torque. That is the change in angular momentum divided by the change in time. If torque is equal to 0, that means that angular momentum is conserved. That it's a constant value. And remember, since angular momentum is a vector, that means it's a constant magnitude and constant direction. And what that basically says, that motion now is confined to being a two-dimensional plane, with the angular momentum of the reduced system mu always pointing in the same direction. And with that, we were able to understand Kepler's second law, in which Kepler said that a planet sweeps out equal area in equal time. Well, by sweeping out equal area, that means that the planet is constrained to always be on a two-dimensional plane. And that's what we observe in astronomy, that the planets going around the sun are each individually on their own constrained to be on a 2D plane. The moon around the Earth is also constrained to be on a 2D plane around us. Now for the planets, they happen to be very close to each other, but not identical. That overall, the general idea is that all the planets are aligned on a 2D plane, but really it's that each planet is always constrained to be on its own 2D plane, and we see here why. By a consequence of writing it, now the interaction, say, of the Earth and the Sun, and by now not looking at both of their individual equations of motion, but the combined equation of motion, no torque can be produced, so the motion of mu is always constrained to be in a plane. And thus, Kepler's second law. With that, we basically saw that Kepler's first law, which we have not defined fundamentally why, Kepler's first law was that all planetary orbits are ellipses. And the basic idea of an ellipse, to remind you, is that it has a major axis and a minor axis. So unlike a circle where the radius is always constant, here the radii are different, where one is larger than the other. This x from here to here is longer in diameter than y, so that would be called the major axis. And a here, from this position, the origin to over here, would be the semi-major axis. And from the origin to this position here would be b, the semi-minor axis. And this is the general shape of an ellipse, where the area of an ellipse is pi a times b. Remember, if it was a circle, then a and b are the same, r, and the area of the circle is pi r squared. So Kepler's first law said that all planetary orbits are ellipses. Because of that, that means you have closest approach and farthest approach to the sun. In fact, even the Earth deals with that. It's not a huge margin, but at closest approach, we're just over 92 million miles from the sun. At farthest approach, we're just under 93 million miles from the sun. Not a big deal, but it is a consequence of nature. Other planets have much bigger differences. But with that in mind, being not completely circular, we have to break up the velocity of mu into two different directions. One, of course, represents the general circular path of an orbit. That is represented by v theta. The v theta here is the same tangential velocity or linear velocity that we talked about in the previous weeks for rotational motion. And that's equal to r times omega. Remember, omega, the angular velocity, is just v divided by r. In this case, I specifically call it v theta in this direction. Vr now can either go outward or inward. And that would represent whether you're, say, getting towards farthest approach. In that case, Vr would point outward. But if you're at farthest approach and now you're getting to closest approach, then it would get back, because your distances are now different. So we just can't deal with the idea of perfect circular motion. We have to deal now with an elliptical motion, where one side is longer than the other. And in doing that, we broke up our two equations into one equation here, and then we saw that those one equation can be broken up into two as well, a radial equation and a tangential equation. The tangential, let me mention it first because it's not needed for this problem, basically says, in this case, that the Coriolis effect is 0. And the Coriolis effect is something that, as I mentioned at the end of our last lecture, deals with a rotating coordinate system, such as the Earth is a rotating three-dimensional coordinate system, where we're on the surface of the Earth, so one of those coordinates, the radius r, just points to the surface of the Earth, and the other two, longitude and latitude, basically a coordinate grid on our surface, but the Earth, of course, rotates. This takes into account that it is a non-rotating coordinate system. So yes, a planet is revolving around the sun, planet's even rotating on its axis, the sun is rotating on its own axis, but the combined mu, reduced mass, is not rotating. So this is not a rotating coordinate system. So that's not needed here. That would only be needed for different types of phenomenon. But what's important here is the radial equation, which basically says ma, remember mu is really ma, minus mu rw squared, or omega squared, and this basically says this equals the central force, and this is just basically Newton's ma, and this right here is the centripetal force. So basically saying ma minus the centripetal force is equal to our central force problem. And that's where we left off last time. So we're already able to see Kepler's second law in both ways. I just mentioned area, but as constrained to be in a plane. But remember, what Kepler also observed, as I mentioned, but could not prove, he just empirically observed this, was that at closest approach, the orbital velocity of the planet was faster, and at farthest approach, the orbital velocity of the planet was slower. With that in mind, let's just go to Newton's equation of gravity, the magnitude. When an object is farther away, when, say, the sun and the Earth is farther away, r squared is greater. If r squared is greater, then the magnitude of the gravitational force is weaker. Any force can be related to ma, and thus the acceleration at farthest approach is smaller, and the velocity of the planet in orbit is less. Contrast that to closest approach. Now r squared is smaller. A smaller number in the denominator makes the magnitude higher, and thus that's related to ma, and thus there's greater amounts of acceleration, and the orbital velocity of the planet is faster. So everything about Kepler's second law can clearly be seen through reduced mass or just through the general idea of Newton's force equation. But now what I want to do is I want to talk about Kepler's first law. And Kepler's first law was all planetary orbits are ellipses. But we have yet to still see why. So, as I mentioned when I was doing my soliloquy in the beginning of Tuesday's lecture, what we're basically doing is we're using algebra to change the situation from a two-body to a one-body problem. And then we're going to use our conservation laws, the conservation of angular momentum as we did here, and the conservation of energy to understand everything else. So basically now breaking up all of the two components into really one component, so that we can get a single scalar representation for the motion. And doing that, now I just want to mention that energy, total energy, and angular momentum, as we saw before, but to remind you again, are constants of motion. So first, by doing this, let me find the magnitude of the angular momentum L. And let me define the magnitude of the angular momentum L as a lowercase cursive l. So that represents the magnitude of it. Clearly the direction is the same, it's always pointing in the same direction. So all we have to say is, in particular, if I called this a x-plane, this was x, y, and coming out of the board was say z, I could just say in particular that L is just equal to L times z hat for full vector rationale. This is the magnitude, and this is the direction, if in fact going up here was pointing in the z direction. Doesn't have to be, but I'm just assuming it is. So the magnitude of the angular momentum I'm going to call little l. And I'm going to do that so that we can have a new representation of this. So remember, basically what we saw for angular momentum based upon this equation